Assalamu alaikum. Hello, everyone. Before we start from where we left off last time, I would like to mention something about the information gain. So the information we gain on a target variable A by knowing the value of an input feature B is equal to the difference between the entropy of A and the conditional entropy of A given B. For different features, the first term here, entropy of A, is constant. Then the one that minimizes the conditional entropy is the one that maximizes the information gain. And the maximum value for the information gain is equal to, on A, is equal to entropy of A. And that happens when the conditional entropy of A given B is equal to 0. When B is telling me everything about A. So in other words, when I know B, there is no uncertainty about A. So then the information gain will be equal to entropy of A. So the information gain here is actually the reduction in the uncertainty we achieve by knowing B. Okay, so we achieve on A by knowing B. So now the lowest value for the information gain is equal to 0. And that happens when the conditional entropy of A given B is equal to entropy of A. And that happens actually when B and A are totally independent. So in other words, when we it happens when knowing B doesn't tell me anything about A. I'm still as uncertain about A as I used before knowing B. So if they are totally independent and B doesn't tell me anything about A, then the conditional entropy of A given B is still equal to the entropy of A, and the difference will be equal to 0. So in fact, the information gain and the conditional entropy are telling me the same thing, because these changes, like this one changes as we change the feature, but this is constant because this relies only on the target variable. So both of them are telling me the same thing. The one that minimizes the conditional entropy is the one that maximizes the information gain. So I can actually make my decision by looking at the entropy. The conditional entropy, the one that achieves the minimum conditional entropy, is the one that is most related to A, or I also can take the difference and look at the information gain. The one that has the highest information gain is the one that is the most related to the target variable A. So now we come to this example. Last time we stopped here. So we load the data of this file, okay, and we create a data frame from that. So we have 4 input features, and we have the target variable or the class label here, okay? Since we are in the context of classification, we call this a class. So we have 2 labels here, true or false. These are the labels, and this is the class, okay? So here we have these 4 input features, as I said, as I just mentioned, and the target variable or the class variable. So our goal here is to calculate the entropy of the target variable, inflated. Then we're going to calculate the entropy of inflated, given we know the value of act. Act is one of the input features. And then we want to compute the information gain by knowing act along with the inflated. So the information gain on inflated, given that we know the value of act. Okay, so how do we compute first the entropy of inflated? Okay, inflated can take like 2 values. So then we have already done that. By now we know this. So the entropy of inflated is equal to the negative of this sum, right? The probability of inflated equal to true times log2 probability of true plus probability of inflated equal to false times log2 probability of inflated equal to false. And in fact, probability of inflated equal to false is not false is nothing but 1 minus the probability inflated is equal to true. So we can also write it in terms of probability of true here. So it's the negative of this sum here. Probability of true log2 probability of true plus 1 minus probability of true log2 1 minus probability of true. Okay, now let's look how we do that with Python. Okay, so before we do that, let me run this cell here. Simply what we are doing here, we are accessing the target variable, the class here, okay, the inflated, okay, and we run this function, value counts. This will tell me how many unique values there or classes and the occurrence of every one. This is a series, okay? So false has occurred 12 times, true has occurred 8 times. Now I can simply compute the probabilities. The probability of false is equal to 12 over 12 plus 8, so 12 over 20, and true is equal to 8 over 20. Or once I computed one of them, the other one is 1 minus the one I computed. So then I get the probabilities. So here, the probabilities is just like the outcome of value counts, and we divide it by the total number of elements. Okay, len of df dot index. We explained all these things. We don't need to waste spend time explaining this again. So now we computed the probabilities. We have two probabilities. Okay, then we just need to call the function entropy. We pass these probabilities, and base is equal to 2. That will compute the entropy. Okay, so and then we get the entropy here. The entropy is equal to 0.97. So the uncertainty is so high. And we can see here, they are almost equally probable here. Maybe this is 60% of the data. For 60% of the data, the class is false. And for 40% of the data, the class is true. So the uncertainty is high. Okay. So here we call the entropy function, which is going to actually compute this equation if the probability is not 0 or 1. And if it's 0 or 1, it's just gonna return the entropy is equal to 0. Okay, that's what this function does. But we also can do it ourselves, right? So if I uncomment this here, simply here, from this table here, from the return of this, the value counts, okay, we can actually compute the number of truths by accessing this one. Okay, we can compute the number of truths and the number of falses, and then the probability of true is equal to the number of truths over the total number. And then if the probability of true is equal to 0 or 1, okay, so the two corner cases, then the entropy is equal to 0. Why we do that? To avoid actually the computation of log 2 of 0, because log 0 is undefined. Okay, so then like we just set that equal to 0. Otherwise, we just plug into this equation here. Okay, and with that we compute the entropy. Okay, so as I said, the entropy is so high, and we clearly see that from here. The uncertainty is high. So if you look on inflated, isolated from any of the input features, then the uncertainty on that target variable is high. Okay, now what we want to do, we want to compute the entropy of inflated, the conditional entropy of inflated given act. Okay, now that is, in order to explain that, I actually wrote all the equations here before we dive into the code. So to simplify it for you. So the entropy of act, the entropy of inflated given act is equal to, so this is conditional entropy, is equal to the probability of act equal to dip, okay, times the conditional entropy of inflated given act is equal to dip, because act is either dip or stretch. So I have these two options. So I want the probability of the first one times the conditional entropy of inflated given act is equal to dip, the first choice here, plus the probability of act is equal to stretch times the condition entropy of inflated given act is equal to stretch. So if act has more choices, then I will have also those here included. So act here has two choices. It's either dip or stretch. Okay. Then in order to compute the entropy of inflated given act, I have to take a weighted sum of these conditional entropies. Okay. The conditional entropy of inflated given dip and conditional entropy of inflated given act is equal to stretch, and then I weight them by their probabilities. Okay, hopefully this clarifies it for you. So the entropy of inflated given act, since act takes either the value of dip or stretch, then I need to compute the conditional entropy of inflated given act equal to dip, and the conditional entropy of inflated given act equal to stretch, and then I take weighted sum between these two. The weights are the different probabilities. The probability of act is equal to dip, and the probability of act equal to stretch. Now, how do we compute this? The probability of inflated given act equal to dip, this one here. This is actually now inflated takes one of two choices or classes. It's either true or false. Okay. Then here when act is equal to dip, we limit ourselves on those data samples. The data samples where the value of act is equal to dip, and we compute the entropy of inflated. Then it's the probability of inflated equal to true, because inflated is either true or false. The probability of inflated equal to true given act is equal to dip times the log 2 of that. Okay, plus the probability of inflated is equal to false. Okay, inflated is equal to false given act equal to dip times log 2 of this probability. Okay, so we condition an act is equal to dip, and we compute the probability of inflated equal to true and inflated equal to false, and it's just like the summation. We do the same for stretch here. Okay, the probability of inflated given act is equal to stretch. Inflated is either true or false for those samples in which act is equal to stretch. So then the probability of inflated is equal to true, given act is equal to stretch times the log 2 of that, plus the probability of inflated is equal to false, given act is equal to stretch times log 2 of that. Okay, now let's look at how we do it using Python. Okay, so let's look at the cross table here. Okay, and then we compute the probabilities from there. We call this table split. So we focus only on these two variables, inflated and act. So let's look at this. Okay, so this is like the counts here. Okay, inflated are the rows, as you can see here, and act are the columns. And inflated can take one of two choices or classes, false or true, and act can also take one of these two choices, dip and stretch. These are the counts, and these are the probabilities. Okay, so this is the probability of false given probability of inflated equal to false given act is equal to dip. Simply act is equal to dip is this column, right? So then when act is equal to dip, inflated is always equal to false. There is no values for truth. So then the probability is 1. 8 over 8 plus 0, that is equal to 1. 0 over 8 plus 0, that's equal to 0. So now this is the first one here is the probability of inflated equal to false given act equal to dip. Now the second column is like has the probabilities when act is equal to stretch. This is the the counts here, the counts, and here are the probabilities. So here the number of samples in which inflated is equal to false given act is equal to stretch. And here is the number of samples in which inflated is equal to true and act is equal to stretch. Okay, now then if I want to compute the probability of inflated equal to false given act is equal to stretch, it will be equal to 4 over 4 plus 8. 4 over 12, that is 1/3. Okay, now if I want to compute the probability of inflated equal to true given act equal to stretch, it will be 8 over 8 plus 4, that's 8 over 12, that's 2/3. Okay, 0.67. Okay, or I just take 1 minus this. It will give me this one. So now I have computed all the probabilities. So if you look at this table here, the first one here is the probability of inflated equal to false given act equal to dip, and so on. You know it now. It's clear. It should be. Okay. Now we want to compute the entropy of inflated given act. So we start first with the first conditional entropy, the entropy of inflated given act equal to dip, this one. We want to compute this one first. Okay, so we have computed it here. Okay, let's work on that one. And we also, in fact, we want to compute both. And entropy of inflated given act equal to stretch. Okay, so the entropy of inflated, okay, given act equal to dip, what are the probabilities? The probabilities are the first column, the dip here. So they are 1 and 0. Okay, because what we want to compute here is the probability of inflated equal to true given act equal to dip, and probability of inflated equal to false given act equal to dip. So which are these two probabilities, 1 and 0. Okay, so we pass these two probabilities. So we are extracting this column when act is equal to dip. So these two probabilities, we pass them to entropy with base equal to 2. Now we have computed the entropy of inflated given act equal to dip. We have computed this. Okay. Same thing applies for the second one. Just we focus, we extract the second column. when act is equal to stretch, this one. So extract that one. Okay, these two probabilities, we pass them to the entropy, okay, function with base equal to 2. Now we have computed the entropy of inflated given act is equal to stretch. Okay, now we have computed this and this, these two, this one here, and this one. So now we want to take weighted sum of these two. The weights are these probabilities. The probability of act is equal to dip and act equal to stretch. We just need to look at the act column. Okay, this is it. So for act column, we run the function value counts and we divide by the length. We get the probabilities, the probability of act and probability of dip. Then now it's done. So then we need just this. We need the weighted sum of these two conditional entropies where the weights are the probabilities we just computed. So then we call the function NP average. Okay, we pass these two conditional entropies and the weights. We want to weight them with these probabilities. Okay, these probabilities. Okay, the first one is weighted with probability for dip because remember the return of this is a series. It's something like this. Okay, so we need to it's just for dip and act, not true and false for the case of you can just run the code later and figure it out. So then we take, as I said, these are the two conditional probabilities and we weight them with their corresponding probabilities. So the probability of dip times the probability of act is equal to dip times this one, the conditional entropy of inflated given act equal to dip plus probability of act equal to stretch times the conditional entropy of inflated given act equal to stretch. This is what's happening here. That's it. We got the entropy of inflated given act, and that's equal to 0.55. So there has been a drop in the uncertainty or the entropy of A, right? So this is the entropy of A, 0.97. This is the conditional entropy of A given B. So this is the entropy of inflated. Okay, this is the conditional entropy of inflated given act. It's less. So that means act is related to inflated. Act is telling me something about inflated. They are not totally independent because there was a reduction on the uncertainty. So then we can just compute the information gain. Okay, so which is the difference between these two, the entropy of A minus the entropy the entropy of inflated minus the entropy of inflated given act, and that's equal to 0.42. That's the reduction in on the uncertainty we achieve by knowing the value of act. Now, one thing left to mention. So here, like this is a concise way to do that computation. We can do it also like this way. It's a longer way. Okay, so I will be very precise here. I will not explain it in details, but let me maybe uncomment it and run it. Okay. So here actually what we do again, so we extract like the relationship between inflated and act in this cross table, so we can look at all the counts and the probabilities. So the first part at very high level, the first part here, by looking at the cross table, okay, we can actually extract the number of times in which inflated is equal to true given act equal to dip. Okay, then we can compute the probability of inflated equal to true given act equal to dip. Then we can compute the first part, the conditional entropy of inflated given act equal to dip, this probability here, because we have extracted everything we need for that. Then we just, instead of passing to function entropy, we can actually do it ourselves. So if the probability of true of inflated equal to true given dip equal to given act equal to dip, if that's equal to 0 or equal to 1, these two corner cases, then the entropy of inflated given dip is equal to 0. Okay, as I said, we don't compute it here because we don't want to run into the error on the computation of log 0, because log 0 is undefined. Okay, otherwise we just like pass to the formula. So this is the first part. It computes the conditional entropy of inflated given dip. Same thing here for stretch. So this is the conditional entropy of inflated given act is equal to stretch. Then once we get these two, we compute the probability of dip and probability of stretch. So we're looking only at that attribute, the act attribute, okay? Simply we compute those, the probability of stretch and dip. And then here we take the weighted sum of these conditional entropies, like entropy of inflated given dip and entropy of inflated given stretch, weighted by their probabilities. Okay, probability of dip times the probability of inflated given act equal to dip plus probability of stretch times conditional entropy of inflated given act is equal to stretch. That's it. So this is like another way to do it, like a longer way to compute it. Okay, we're not using the entropy built-in function, or like we're not calling the NP average and passing the weights. So we're doing everything from scratch. Okay, but leads to the same result. Okay, so how do we construct a decision tree? Now we explained the uncertainty, how to compute the entropy and the information gain, then how we use this to construct a decision tree. Okay, as I already mentioned, like, okay, let's maybe read these 3 steps and then go to the example. Okay, so the first step, we calculate the entropy of the target variable. Okay, the class variable. Okay, here in the context of classification, we call it the class. Okay, so the class variable has like number of labels. Okay, everyone define a separate class. Okay, we calculate the entropy of that variable. Then we calculate the information gain or the conditional entropy. Okay, we will calculate actually the conditional entropy, and then from that we can rely only on the conditional entropy, or we compute the information gain. Okay, like of the target variable given every input feature. So we will go over every input feature. We take that feature and we compute the conditional entropy on the target variable given the value of that feature, and we compute the information gain. The one that maximizes the information gain is the one we will choose at that node. Okay, choose the feature with the largest information gain as the decision node. Divide the data by its branches and repeat the same process on every branch. We're gonna come to explain. It's maybe if we look at that visually, it will be easier to understand. Okay, let me load this data. Again, it's the same file. Okay, so these are the 4 input features we have, and this is the target variable. So in total, we have 20 samples, and for every one of these features, there are only 2 choices. Okay, and this is like all of them, as I said, are categorical. Okay, here there is no order. Here, small and large. Okay, that is debatable. We could say there is an order. We could say there's no an order. Okay, so here we will treat it as there is no order. Okay, so we will just use one hot encoding for all of these features. There's no order here. There's no order here, and that's the class level. We will also encode it using numerical values, because actually we're gonna use a built-in function from scikit-learn. We're gonna come to that. Okay, let me just not be ahead of the slides. So here we have these that are the input features, and this is the target variable. So from scikit-learn.tree, we import decision tree classifier and plot tree. This we will use to build the classifier, and here we use the plot tree. We use it to plot the outcome, the tree. Okay, so here we create the object, the classifier object. Okay, the criteria we use is the entropy, and we pass this argument here. Splitter is equal to best. We will choose the feature that achieves, like that minimizes the entropy, that achieves the lowest conditional entropy or highest information gain. Okay, random state is equal to 0. This is just for the reproducibility. Okay, so we need, every time we run the cell, we reproduce the same results, because if you have 2 features, they lead to the same reduction. If you run this cell again and again, every time you may have like different trees. Okay, because at a given level they are equally likely. They have this, they achieve the same reduction. So sometimes the code choose based on the random state, Sometimes it chooses this or that. So then we want to make sure that we produce the same tree. So we fix the seed here. So here we created the classifier, the object, okay? Here we actually performed one hot encoding uh, for all of our variables, including the target variable, okay? And we drop the first for everyone. So we are replacing these features with the same number of features, but they will be numeric with values 0 and 1, okay? So when we're dropping the first, for example, take one of them here. Inflated, like when we run one hot encoding here, we will have inflated underscore true and inflated underscore false. And since if comes before t in the alphabetical order, then inflated false will be first, inflated underscore false, and then inflated underscore true. We are dropping the first one, we will drop inflated underscore false, then we will end up having inflated underscore true. And the same thing applies to every other one. So we will have one, every feature here will be replaced unless it, okay, each one of them has two choices. So then we will actually have the same equal number of features. They are just numeric features. Maybe let me print it here or display it. Okay, before we even go to the next thing here. This is it, okay? The same number of features, the value is either 1 or 0, okay? For example, take this one of them, age underscore child, okay? So this is equal to 0 when the age is equal to adult, because age is either adult or child, okay? When it's equal to 0, that means for this sample, the age is adult, it's not child. It's equal to 1 when the age is equal to child. Okay, hopefully it's clear to everyone. We have been working with one hot encoding, so we know it very well by now. So here we created the classifier. Here we encoded all of our input features to numeric values because this the decision tree classifier takes numeric data. It doesn't work with categorical data. In fact, if you want to build your tree yourself from scratch, you can actually, because our trees, like we will need to compute the entropy and all of these things in order to find which feature to choose, but we still can actually build our tree based on the categorical values, because all we do is conditioning. So we are checking conditions. We can still condition on the non-numeric data, but here, since we are using the built-in classifier, we have to do this transformation. Okay, so here we created the classifier. Here we encoded our data into numerical values. Here we fit the classifier in our data. Okay, we pass all the input features here. So we drop the target variable and we pass the target variable here. So here, by running this line, we have actually computed that, found the tree, the decision tree. Okay, let me do it. Let me start by this. Okay, so here we are plotting the tree. Let me look at the tree with you here. We are plotting the tree. This is the tree. Okay, so now here, if you look at this tree here, like x of 3, which is the third feature. Okay, so then I need to every time go back and see what is x of 3. So then if I actually pass this here as an input argument, I don't need to do that. The features will be printed in the tree. So feature names is equal to all columns after dropping the last one to list. Okay, so these are my feature names. Then if I rerun this here, I will actually, this has been replaced by the feature name. So here, like the first condition here is checking age underscore child less than or equal to 0.5. What's that supposed to mean? So when this condition is satisfied, when this is true, we go to the left. Otherwise, we go to the right. Okay. So now when we go to the left, that means age is not equal to child. When age is not equal to child, because age is equal to child, when age is equal to child, this is equal to 1, which is greater than 0.5. But when it's less than or equal to 0.5, that means age is not child, or in other words, age is equal to adult. So when age is equal to child, we come here. Okay. When age doesn't equal to child, when this condition is satisfied, when age is not equal to child, we come there. And it turns out like the age has the highest one. It's either the only one that has the highest information gain or one of them. Okay, this could have the same information gain, but because one of them has to be chosen, then with this random seed, this has been chosen. Maybe if we change the random here, seed to 91, I believe I checked this in the past, age and act, they have this, and now it's act, because they have the same reduction in the conditional entropy or the same information gain. Okay, let's stick with that for now. We want to also print out the class names. So let's add this here. Okay. So here, false and true. We are plotting the class names here. So if I want to stop here, if I don't want to continue, then the class, I will do majority vote. And since 60% of the samples are of class false, then I will choose the class is equal to false if I don't want to run any model. Okay, so now if I run this condition, okay, this condition, checking the age, okay, so 12 samples came here, 8 samples came here, okay. Now, all of these 8 samples are belong to, for all of these 8 samples, the value for the target, for the class label is equal to false. So all of them are belong to class false, class F. So then if this is clear separation between the two classes. So every sample that comes here belongs to class F. So this is the total number of samples that came here. Samples is equal to 8, and all of these 8 are belong to class F. Let me explain something I forgot to explain here. The entropy here on the target variable is equal to 0.971. There were 20 samples. 12 of them belong to class false, 8 of them belong to class true. Okay, after running this condition, 12 samples came here, 8 samples came here. For these 8 samples, there is no uncertainty. The entropy is equal to 0. Okay, all of them belong to class false. Okay, so this is a leaf node. If I reach here, then I know the class. Okay, now for this one here, for the samples that came here, okay, the entropy is equal to 0.918. Okay, and the number of samples is equal to 12, okay? And there's still confusion between the two classes, the false and true. But the majority are from class true. So if I want to stop here, I don't want to continue, I do majority vote, I will choose class true for all of these samples here, the 12 samples. 2/3 of the time, I will be correct because 8 samples are belong to class true, but 1/3 of the time, I will be wrong. So if I stop here, I will run into an error 1/3 of the time. Okay, then I still can check on the, now this is all of this what I have said before looking at this condition. All of these here, the entropy, the number of samples, the values before looking at this condition. It's after looking at this condition here. This is what we get. Now, if we look at this condition, act, now we don't need to look at any condition here. We reach the leaf node, we reach the class, we reach a clear separation here. Okay, we don't need to check further here. That's it, done for this part, for this branch. Here, I will check, I will compute, find the feature that minimizes the conditional entropy the most or achieves the highest information gain, which tends to be the act. Okay, so then the condition we built here is act underscore switch less than or equal to 0.5. Okay, because now we have this here, act underscore switch. That's the function, that's the feature we have here. It's equal to 1 when act is equal to stretch, 0 when act is equal to dip. Now we're checking that condition. Now it turns out like 4 samples satisfy that condition. Okay, the value for act was dip, was not stretch, because act underscore stretch is less than 0.5. So for 4 samples came here, satisfied that condition, and 8 samples did not satisfy that condition, they came here. We come here when this condition is satisfied. So if it's true, we come here. If it's false, we come there, if this condition is not satisfied. And it turns out like here we have a clear separation. Okay, here all of the 4 samples that came here, they belong to class false. Okay, when we do majority voting here, we get a class equal to false. Okay, and all of the 8 samples that came here, they all belong to class true. So we have a clear separation here between these two classes. So then with that, we stop, okay? Because now we reached leaf nodes everywhere. So the stopping, we either stop if we reach clear separation, or if we have tried all the features, we stop after that, even if there is still confusion, because that's the best we can do, okay? That is, now let me just do something, add this here, filled equal to true and raw true. Okay, that's the last thing to add. Okay, and look at what does it tell us, okay? If you look at this here, okay, so round is just rounding the corners, okay? But filled is an interesting one. So here, the ones that belong to class false, for those ones, we have clear orange color. For the ones that belong to class true, we have a blue color. Now, if there is a confusion, we will have a color that is between these two, orange and blue. So this is more of orange than blue here, because there are more samples belong to class false than class true. Here it's more of a bluish, because there are more samples that belong to class true than belong to class false. So by looking at the color, you can tell if there is a clear separation or if there is a confusion, and if there is a confusion, it's closer to which one of these classes. Okay, so now let's look at like decision rules we can extract from this. Decision rules is like after you build the decision tree, you can actually write it as a set of classification or decision rules. Okay, if you have condition and then there is a result. Okay, so rules are popular alternatives to decision trees. Rules are typically of this form. Okay, so one rule, one individual rule is not a model. The model is actually a set of rules. Okay, these rules are derived from the decision tree by following the paths from the root node all the way to the leaf nodes. For every leaf node, there is a rule. For example, what's the rule for this one here? If age is equal to child, then inflated is equal to false, right? Here, if age equal to child, then inflated is equal to false. Now, let's look at the rules that are associated with these two leaf nodes. Okay, let's look at this one here. Here, if age is not equal to child, in other words, if age is equal to adult and act is equal to dip, then inflated is equal to false. If age equal to adult and act equal to dip, then inflated is equal to false. Now here, if age is equal to adult, I come here, and act is equal to stretch because I come here if this condition is not satisfied. And this is not satisfied when act is equal to stretch. Okay, because when act is equal to stretch, that means act stretch is equal to 1. That is greater than 0.5. So we come here. So when age is equal to adult and act is equal to stretch, inflated is equal to true. That's the last one. If age is equal to adult and act equal to stretch, then inflated is equal to true. Okay. We will stop here for today. Okay. Yeah, let's stop here for today and we will continue from here next time. Thanks for watching and see you next time. Salam alaikum.